In this video, we're going to introduce the thing that really gives all the work we've been doing with standard normal distribution its power. It's called the central limit theorem, and it's based on the idea of getting an estimate for the population mean from a sample. So the story that we want to talk about, Chifaru wants to know, on average, how many Facebook friends her real friends have. But she doesn't want to spend all of her time and bother all of them to ask them about this. So she tries to figure out what's the most efficient way of estimating her mean number of Facebook friends. Well, but she doesn't want to start from inventing the wheel, right? So she flips through her stats textbooks to see what that can tell her about it. So she sees that all the estimating techniques that we have require a simple random sample. So the definition that's in the book is a little cumbersome. It says a simple random sample of size n is chosen by a method which every collection of n population items is equally likely to make up the sample. And its example is a lottery. But a more straightforward way to think about this is that every individual in the population has the same chance of being part of the sample, right? The simple random sampling simply means that everybody in the population has the same chance of being in the sample, right? And every member has the same chance of not being in the sample. There is no control over who is and is not. It is purely random chance. All right, so Chifaru now makes her list of friends and is ready to take her random sample. But how big should this sample be? Logically, the more that we have in the sample, the better an estimate it can be. But the more that's in the sample, the more work she has to do, the more friends she has to bother, the more time she has to put in. So what does she do? Right, again, she ideally wants it to be big enough to be useful, but small enough so that it's easy to do in a reasonable amount of time. So she looks through a book and sees that if our sample size is greater than 30, right, we can use what she knows about the standard distribution, right? So greater than 30 it is. Okay? All right, so let's introduce the big theorem. All right, so this is our big one. It's called the central limit theorem. Right? So let x bar be the mean of a large sample, right? Simply more than 30. It has to be a simple random sample, right, from a population with a mean and a standard deviation that are known. Okay? Then the mean for that sample has an approximately normal distribution. That means that this data point comes from a standard normal distribution. The mean of that normal distribution for the samples has the same mean as the sample. And the standard deviation is actually shrunk quite a bit. The standard deviation for the sample distribution is shrunk by the square root of the size of the sample. So the peak gets narrower based on the size of the sample, but the mean doesn't move at all. All right, so what does the central limit theorem tell us? Okay, it tells us that if we know the population mean and the standard deviation, then any sample large enough is going to come from the standard normal distribution with this as the mean of the sample distributions, and the standard deviation is shrunk by the sigma over the square root of n for a sample size. That means for such a sample of size n, 95% of the samples will be within 2 sample standard deviations of the population mean, right? So within 2 of these guys of our population mean, our mu. And this also gives us something a little cooler. The population doesn't need to be normal. As long as the samples are large enough, the means of the samples are going to be coming from a standard normal distribution. So we can use all of our tools for the standard normal distribution to tell us something about our sample mean and its relation to the population mean. Right? So the central limit theorem is powerful, but it doesn't tell us everything. If we take a sample and we get a sample mean, we don't have any idea exactly where in its distribution the sample mean is. Right? So even in our best possible case, our sample mean is not guaranteed to be a good estimate of the population mean. It's just a measure of that it's going to be likely to be a good estimate. Okay? And we will talk about what can go wrong in a little bit. And also, if we don't know the population mean and the population standard deviation, we need to estimate these. And we're going to do that fairly soon. But in general, if we're actually taking this data for these samples, it's because we don't know the population mean and the population standard deviation. So these estimates are going to be very powerful. Okay? But for the moment, let's work with the tools that we have.